This is my third video about the best methods for reducing ketones to secondary alcohols. The main subject of this presentation is the Meerwein-Ponndorf-Verley reduction. This is a highly selective method for reducing ketones which is often used in the perfume industry. The Meerwein-Ponndorf-Verley reduction is the reversal of the Oppenauer oxidation, which I had already presented in an earlier video. In this reaction, a ketone is treated with an excess of a primary or secondary alcohol in the presence of an alkoxide catalyst, whereby hydride is transferred from the alcohol to the ketone. Aluminum alkoxides are most commonly used, but zirconium alkoxides also seem to be well suited. These alkoxides are not too basic and do therefore not catalyze aldol chemistry as effectively as, for instance, magnesium or sodium alkoxides. This type of reduction only requires inexpensive reagents and solvents and is usually quite easy to perform. High chemoselectivity and the absence of smelly byproducts are further advantages of this reduction strategy. Problematic is the generation of at least one equivalent of a ketone byproduct, and that usually an excess of alcohol must be used because the reaction is reversible. The reported amounts of catalyst are often quite large, but in some cases a more careful optimization allows the reaction to proceed with much less catalyst. Because of the reversibility of the reaction, secondary alcohols will epimerize to a certain extent, what can be a problem when a high stereoselectivity is required. This is such an example where a high degree of diastereoselectivity was necessary. Fortunately, the product was quite resistant to base-induced epimerization and a high yield of the desired diastereomer was obtained, despite a reaction time of 15 hours at 50 degrees Celsius. Instead of aluminum alkoxides, mixtures of an alcohol with trimethylaluminum can also be used, as shown by the example on this slide. With this catalyst, the reduction already proceeds at room temperature, and even base labile ketones, such as phenacyl chloride, give high yields of the expected alcohol. This is an example of the optimized reduction of an alpha-beta unsaturated aldehyde. Aldehydes are usually easier to reduce than ketones, but do also readily form condensation products with the acetone formed. Still, in this case, a good yield of allylic alcohol was obtained. Less selective reducing agents would have probably also reduced the electron-deficient alkene. Ruthenium complexes are not only suitable catalysts for the hydrogenation of ketones, but can also mediate Meerwein-Ponndorf-Verley reductions efficiently. I have sketched the mechanism of this reaction in my video about the Oppenauer oxidation. In the example on this slide, 1,4-butanediol was used as hydride donor and was converted into butyrolactone during the reaction. Only a small amount of base and catalyst were required, and the yield of the target alcohol was high. Because this type of reduction is base-catalyzed, other base-mediated reactions may occur simultaneously. These include aldol addition and condensation, beta-elimination of alkyl halides, and the isomerization of reactive double or triple bonds. Also, epoxides can be isomerized by bases either to allylic alcohols or to aldehydes or ketones, which would then be reduced to alcohols. Aldehydes can also be dimerized to esters by catalytic amounts of bases in the so-called Tichenko reaction. Finally, as already mentioned, due to the reversibility of this reduction, secondary alcohols may epimerize and cause the formation of mixtures of diastereomers. This is a list with some further examples, also with other catalysts than those already mentioned. Interestingly, the first entry is an example of a catalyst-free, purely thermal reaction. This required, however, 300 degrees Celsius, what is not really compatible with most starting materials.